Good morning, class. I've got slightly different technology today. I forgot to bring home the tablet that I was using before, but we'll just make do without handwriting recognition. So today's lesson is our first collisions lesson. We actually did this before, but I wanted to make a video about it. So what we're going to study in this section is collisions in one dimension. Collisions in one dimension. Later we'll do two dimensions. There's really not much difference except that in one dimension we don't have to worry about the x and y coordinates of things. Everything is going in the same direction. In other words, a collision in one direction basically looks like you've got, say, a ball, and it's traveling towards another ball over here. Gotta get used to this slightly different tablet. And that would be, say, your before situation. Okay, so that would be before. And then your after situation might look something like this. Say you've got one here and one here, and this one's moving like this perhaps, and this one's moving like this perhaps. So this would be our after. So the thing about these collisions is that one of the things you always have to know is it an elastic collision or is it an inelastic collision? So we have two possibilities, elastic or inelastic. Okay, in an elastic collision, you have, well, first of all, in both of them, momentum is conserved. So P initial equals P final in both cases. P initial equals P final. But elastic also has kinetic energy initial equals kinetic energy final. That would be like typically like two pool balls smacking into each other. When they bounce off, it's almost a perfect, there's no energy loss. There's the same amount of kinetic energy initially in the first ball as there is finally in both balls combined. Whereas in an inelastic situation, kinetic energy initial is always greater than kinetic energy final. That's because you've got, when they smack together, some energy is lost. It's possible that they heat up, and there's where the energy goes. Or one or both of the objects deform, just smash. They might even stick together. If they stick together, we consider it most completely inelastic. So basically, you could think about if you had a ball and the ball was inflated really hard, that would be more like elastic. If the ball was practically flat and very soft, that would be more inelastic, the way it bounced. And you know, if you bounce a ball that's inelastic, it loses a lot of energy. It hardly comes back up at all. Whereas if you bounce an elastic ball, it'll bounce right back up. So let's see how we could actually solve a problem. Let me make a new page. All right. So I want you to go in your book to page 205. We're going to look at example 7. Okay, so if you need to pause this video to go get your book, you can go ahead and do that. What we've got in this story, you can see, is we've got a picture of before collision. Okay, so we've got a small ball and a large ball. And we can see that the small ball is headed towards the large ball. And in fact, this one has a mass of m1, this one has a mass of m2, V02 equals 0 meters per second. This one's not moving at all. And then this one has V01, the velocity of the first one. Then we have, so this is our sort of initial situation. Then we have our final situation. In our final situation, we've got the small ball and the large ball. And in this case, they're both moving. The large ball is moving to the right, and the small ball is moving to the left. So here we have V final 1 and V, final 2. So let's see what we're given as information. One ball has a mass of m1 equals 0.25 kilograms, okay? Equals 0.25 kilograms. Initial velocity of 5 meters per second. I don't know why I've got this hand here. Equals 5 meters per second. The other mass has a mass of 0.8 kilograms. And it is at rest, so its initial mass is 0. No external forces act on the ball, so that's why we can have our conservation of momentum. We're also told it's elastic, so we have conservation of kinetic energy. What are the velocities of the balls after the collision? So we're going to end up with two equations, one for kinetic energy and one for momentum. So let's see. Our momentum equation, okay, the equation that says delta T equals 0 is going to, I don't know why I keep getting that. Is going to look like this. M1 V01 plus M2 V02 equals M1 V final 1 plus M2 V what is causing that to do that? V final 2. An eraser. Yeah, here's one. All right, so let's see what these things are. Well, M1, that's 0.25. If I use this one instead, does it matter? That's a little thick. I prefer this one. So I could use this one and set it for thinner. Okay, so we got 0.25, that's pretty good. V01 is 5, okay. Now, we know that V02 is 0, so this term is going to go away. Okay, So that's going to be equal to M1, which is 0.25 times the final one plus M2, which is 0.8 times the final 2. Let's see. 0.25 times 5 is 1.25 equals 0.25 the final 1 plus 0.8 the final 2. What is causing that to do that? Maybe I should pause it for a second and try to figure out this problem. Okay, I think we got the problem figured out. Now, the next question is, so there we have our first equation. That's our equation for momentum. Now, let's see. I can actually use this thing, now that I understand how to work it, to move this up. And we're going to do conservation of kinetic energy, right? Because the change in kinetic energy is also equal to 0. That's 1/2 m1v squared plus 1/2 m2v squared. Okay, so 1/2 m1v squared plus 1/2 m2v squared, and this is, we'll call that V0, 1, and V0, 2, has to equal 1/2 m1 the final 1 squared plus 1/2 m1 the final 2 squared. So let's see what we have here. That's 0.5, that's 1/2. M1 is 0.25. V01 is 5 squared plus, now we know that V02 is 0, so this goes away. So actually, instead of calling it plus, I'm going to erase that, and I'm going to say that has to equal 1/2 m1 v final 1 squared plus 1/2 m2 v final 2 squared. One thing I'm thinking as I look at this, I'm thinking you got a half, a half, a half, right? If we multiply both sides by 2, we can get rid of all the halves. Okay, so now 5 squared is 25. 0.25 times 25, 0.25 times 25 is 6.25. So here we have 6.25 equals m1 v final 1 squared plus m2 v final 2 squared. So now we basically have two equations. Oh wait. Yeah, we know those M1s and M2s. So actually, I'm going to write this over again. I'm sorry. Okay, let's redo this. Because M1 is 0.25. 0.25 V final 1 squared plus M2 is 0.8 V final 2 squared. Okay. So now we have our two equations. Okay, we've got that equation and we've got this equation. I'm going to pause it and I'm going to put those equations on my next page. Okay, so here we go. You can see that we've got two equations with two unknowns, V final 1, V final 2. Those are the two things we're trying to find out. This is a mess, but it's just a substitution problem. So what I suggest is we go with the linear equation, this one here, and we solve it, say, for V final 1, all right? So, for instance, we could say 0.25 V final 1 equals 1.25 minus 0.8 V final 2. Now, if we divide both sides by 0.25, we'll get V final 1 equals 1.25 divided by 0.25, that's going to be 5, minus 0.8, 0.8 divided by 0.25, that's 3.2, 3.2 VF2. All right, so then we take this expression right here and we substitute it in for VF2 right there. So then we rewrite the second equation with that expression in there. And we have 6.25 equals 0.25 VF1. Oops, I'm sorry. We're not going to substitute it in for that. Let me change some things here. We're going to substitute it in for VF1. So let me go back to here. Sorry about that. How many of you caught that? Right, we solved for VF1, so that's what we have to substitute it in for. So here, instead of VF1 here, what we're going to put is 0.25 times 5 minus 3.2 VF2 squared equals, right, is that right? Yeah, so that's, the whole thing is squared. Plus 0.8 VF2 squared. I haven't done this problem before, so we'll see where we end up. But we've got to square this piece here. Now, those of you who have algebra should remember this is going to be 5 squared minus 2 times 5 times 3.2 VF2 plus 3.2 F. This is going to be A squared plus b squared is a squared plus 2ab plus b squared, okay? Or a minus b squared is a squared minus 2ab plus b squared. All right, so this is going to be, so 6.25 equals 0.25 times 25, that's squared. Now, minus, we've got 5 times 3.2 times 2, that's going to be minus 32 VF2 plus 3.2 squared, 10.24 VF2 squared plus 0.8 VF2 squared. This is crazy. I wonder how they did it. Let's look here and see what they did. I'll pause this for a second. Well, they don't really show how they solved it. We can solve it by brute force and graphing calculators. Let's just go ahead and do that. I wouldn't expect you to have to do this problem. This is just way too crazy. But let's just see what we have here. We got our 6.25. Now we got 0.25 times 25, 0.25 times 25. That's 6.25. Minus 0.25 times 32, 8 VF2. Now we got 0.25 times 10.24. .56 VF2 squared plus 0.8 VF2 squared. So subtract 6.25 from both sides. Maybe it's not that bad. Yeah, it's not that bad. 0 equals, we got a VF2 here and 2 VF2 squared there. So that's going to be negative 8 VF2 plus, let's see, 2.56 plus 0.8, 2.56 plus 0.8, 3.36 VF2 squared. All right, so if we factor a VF2 out of both sides of the equation, we end up with 0 equals VF2 times negative 8 plus 3.36 VF2. All right, so either VF2 equals 0 or it's the solution to this here. I'm going to choose this solution, okay? So I'm going to say that 0 equals negative 8 plus 3.36 VF2. So that means that 8 equals 3.36 VF2. Divide both sides by 3.36. Okay, so we've got 8 divided by 3.36. So 2.38. So this says that VF2 equals 2.38 meters per second, and which is exactly what they got, amazingly. And we can use this to get VF1, right? VF1 equals 5 minus 3.2 times VF2, 2.38. Okay, which is equal to 5 minus 3.2 times 2.38, which is 2.62, negative 2.62. 2.62 meters per second. All right, so there is our answer. I know, they're nasty. Everybody hates these. But that's how it is. So basically what we've got is we can see that what happened was the balls came together and then they bounced up back, right? So you can see that initially, finally V02 is to the right and VF1 is to the left. Let's see if that's what we got. Yep, VF1 is to the left. Right? Hold on a minute. I can minimize this thing. So that's that problem. Huge, crazy. So let's look at the basics of what we did here. All right, I'm going to go back to the first page just to review. There we go. Okay, so we have a situation with two balls in collision. This ball moves to the right and hits this ball. They bounce off of each other. And we're told that we have an elastic collision, which means the kinetic energy change is 0. So here we go, and we've got, we say this is the momentum initial equals the momentum final. And you can see there was no momentum initial for the second ball because it wasn't moving. And then we say kinetic energy initial equals kinetic energy final, and there also was no kinetic energy initial. And what happens here is you end up with a linear equation that comes out of the momentum conservation and a quadratic equation that comes out of the kinetic energy. In other words, what I'm trying to say is they got squares in the one with kinetic energy, and they don't have squares in the one from momentum. So I'm going to solve the simpler one, the one without any squares in it, and then substitute the answer. So here we take the simpler one right here. We solve it. Just, in other words, in this case, I solve for V final 1, all right, in terms of V final 2. Plug that back into V final 1 in the second equation. Okay, so here it is plugged back in, 6.25, and this in parentheses here, 5 minus 3.2, VF2, that's this right here, that's what we got. And then we just have to deal with this thing, and if you're lucky, you end up with a nice situation like this where we can factor out one factor of V final 2. So we're saying either V final 2 is 0 or V final 2 solves this equation here, because if two things multiply together to get 0, then that must mean that one of those two things is 0. It's interesting that there are those two solutions. I have to think about that more to think about why that really works. What would happen, for instance, if we decided it was 0? Let's see. If VF2 really were 0, then VF1 would be 5. So that's interesting. It just doesn't seem likely, right? If we look back here, if this was 0, this thing went right on past at 5. So in other words, that would be the situation where they missed. There really was no collision, which doesn't happen in our case. So the equations don't really tell us that a collision happened. If it did happen, then they bounce back. If somehow this one passed straight through that one, it would keep on going at 5, and that one wouldn't move at all, and momentum and kinetic energy would still be conserved. So that is a solution to the equations. It just doesn't match the reality that we know about. Okay, so that's what we have for a collision in one dimension that has and elastic, so kinetic energy is conserved. Let's just see what would happen if we did that same problem, except this time we said they stuck together. I think what we would find would be the whole thing would be a lot easier. So let's start over again. Okay, this time we have the same initial situation. We have a small ball going towards a large ball. Okay, so we've got an initial velocity, and we have the same settings. Let's see. M1 is equal to, let's go back to the beginning here on the previous page. We're told M1 is 0.25 kilograms. Whoops. 25 kilograms. V01 is 5 meters per second. And M2 is 0.8 kilograms. So let's make a new story. In this story, in the end, they're stuck together. Okay, so they're stuck together. This is a completely inelastic situation. And we've got this V2. We don't know what it is. So because it's inelastic, that implies that kinetic energy is not conserved. That's going to make this problem a lot easier because we've got no squares in here. We have only one equation. We're just talking about conservation of momentum. Okay, we're talking about the fact that the change in momentum equals 0. So let's see what that tells us. That basically tells us that M1 V01 plus M2 V02 equals M1 V final 1 plus M2 V final 2. So, in our case, we've got, let's see, what was that, 0.25? Yeah, okay, so we have 0.25 times 5 plus, this is 0 because the second mass is not moving. Now, these two masses are together. Okay, so we've got, let's see, we've got a 0.8 and a 0.25, right? So that would be 1.05. I'll just double check that. 0.8 plus 0.25. Yes, so our final mass is 1.05, and that's multiplied by our final velocity. Much easier, right? So basically, if we divide by 1.05 here and 1.05 here, we get that V equals 0.25 times 5 over 1.05. 0.25 times 5 divided by 1.05 is 1.19. 1.19 meters per second. There's our answer. So you can see that when you bring in that elastic collision with the conservation of kinetic energy, the things get way, way more complicated. But it's not too bad in a situation like this. How about if I make one up for you to do? Okay, here we go. Let's imagine that we've got two masses, okay? So here's our first mass, here's our second mass. Okay, so we'll have our first mass, M1 equals 10 kilograms, and our second mass, M2, equals 2 kilograms. And let's say that V01 equals 3 meters per second, and in the end we're going to end up with a situation where the two masses are stuck together. Whoops. Okay, and the question is, V final equals question mark. So why don't you go ahead and pause it and try that problem yourself. Okay, I'm back. I'm going to give this a try. So basically what we know here is, all we know is that the change in momentum equals 0. So that means that M1 V01 plus M2 V02 equals M1 V final 1 plus M2 V final 2. In our situation, that's going to mean that 10 times 3 is going to equal 10 plus 2 is 12 times V final. So 30 equals 12 V final. V final equals 30 divided by 12, which is 2.5 meters per second. Okay, now, one more thing I want to look at here. So, first of all, it slows down, which makes sense, because there's only a certain amount of momentum here. It was originally moving 10 kilograms, now it's moving 12 kilograms. So you're going to imagine that this velocity is going to have to go down, so that makes sense. And in effect, you can sort of see what's going on. 10 times 3 is 30, okay? So the question is, what times 12 is 30? And the answer is 2.5 times 12 is 30. The momentum stays the same. So that's our whole lesson for today. Basically what we've got is we've got collisions in one dimension. And if they're elastic, then we have conservation of momentum and conservation of kinetic energy. If they're inelastic, we have conservation of momentum, but not conservation of kinetic energy, because kinetic energy is lost. Inelastic would be the case of, say, a ball that's not well inflated, or a collision between two cars, or two things that actually stick together like two pieces of clay. So that's all I've got for you for this lesson. You have problems to solve on that, which I think you already did. And then I'm going to give you another lesson on two-dimensional collisions.